Okay, so my talk consists of 3 parts. The first part is devoted to the boundedness criteria for the multilinear Riesz potential operators from the product of Lorentz spaces to another Lorentz space. Another part, the second part, it is dedicated to the Olsen's inequality, sharp type of Olsen's inequality. And finally, we will discuss criteria for the weighted boundedness of one-sided multilinear fractional integrals. So in the last 2-3 decades, it was attracted considerable attention of researchers to the study of problems of harmonic analysis, more precisely operators of harmonic analysis defined on sets on quasimetric measure spaces with non-doubling measure. So such investigations were initiated in the papers by Nazarov, Trail, Wahlberg, by Javier Tolsa for singular integrals, by Garcia Cuerva, Gatto, Garcia Cuerva, Martel, by the speaker with Vachtan Kokilashvili, by Thomas Hutonen for fractional integrals. Okay, such spaces, I mean that quasimetric measure spaces with non-doubling measures, they are called also non-homogeneous spaces. In the most of these papers, the results are obtained under the condition that a measure satisfies so-called mild growth condition or polynomial growth condition. So we will discuss today such a problem in the setting of Lorentz spaces. Okay, so everybody, for everybody, it is familiar the Riesz potential operator given by this formula defined on Rn, and this operator plays an important role in harmonic analysis, in PDEs, especially in Sobolev embeddings. The study of a multilinear version of this operator, so-called bilinear fractional integral operator, given by such a formula, it is given in bilinear form. Okay, f and g, they are measurable functions. We have here product, and then it is divided by modulus by the norm of t to the power n minus alpha. Okay, integration it is over Rn, and it is bilinear form because depending on 2 functions f and g. So such operator was introduced in the paper by Grafakos in 1992, and it was also studied by Grafakos, by Koenig, Stein, and other their collaborators, the mapping properties of such operators in Lebesgue spaces. And as an intermediate operator between that bilinear operator and Riesz potential operator, it is just such a multilinear fractional integral operator given by such a formula written in M linear form. Okay, we have here the product f1 and so on fm divided by you see we have here the sum, x is fixed. Sorry, I don't need, yes, x is fixed. Integration, it is on Rn, and so this, in fact, here is misprint. I apologize. Here is Rn to the power m.
Yeah.
Yes, because y1 and so on ym, they belongs to Rn. That's why we have here this set of integration. So so we considered analog of this operator in quasimetric measure space. So it is given this operator here for quasimetric measure space. So x d mu, it is a quasimetric measure space. This means that x is a topological space. D is a quasimetric defined on X. Mu is a complete measure. Okay, and it is assumed that all balls by this quasimetric are measurable. They have finite positive measure, all balls. And so if we write now such an operator given by this formula, okay, then of course there arises a question of the boundedness of this operator from the product space into another product space. I mean function space, from product of function spaces to another function space. Okay, and as I mentioned initially, we studied this problem for Lorentz spaces. Currently, we studied for Lorentz spaces. Okay, and in the linear form, so that operator is such an operator given by this formula. Okay, and we have as a consequence also characterization of those measures or necessary and sufficient condition on measure mu, for which this operator, it is bounded from one Lorentz space defined with respect to this measure into another Lorentz space. Okay. So in particular, we have characterization for this inequality. Characterization, I mean that necessary and sufficient condition on measure mu. Regarding this problem for classical Lebesgue spaces, it was studied by the speaker with Vakhtang Kokilashvili in the beginning, as I mentioned, in the beginning of this century, and simultaneously such a problem was studied by Garcia Cuerva and Martel in the multilinear setting. In Lebesgue spaces, it was characterized by the speaker jointly with Kokilashvili and Mieczyslaw Mastilo. It was published in Journal of Geometric Analysis in 2020. And now we will deliver our results in Lorentz spaces. So this is the definition of quasimetric measure space. As we see here, the D is a quasimetric with a quasimetric constant K, okay, and mu is a complete measure. We say that mu, it is alpha upper beta regular if there exists a positive constant B0 such that for every X and for every R, this condition here, it is satisfied. This condition that the measure of every ball, such a ball, it is estimated by this constant B0 R to the power beta. Okay, it is called also growth condition, polynomial growth condition. Okay, what about now spaces in which we are interested? This is a Lorentz space depending on two parameters, P and S, defined with respect to mu, measure mu. So this is given by such a norm given on the screen. This is the case when S, the first line we have the case when S is finite, and in the second line we have the norm in the case when S is infinity. In fact, when S is equal to infinity, it is a quasi-norm, in fact. Okay? And mu, here we have distribution function of f with respect to mu to the certain power multiplied by such a function and take an integral from 0 to infinity. So if this integral is finite, then we say that f belongs to the Lorentz space. In particular, when we have one and the same indices here, the P is equal QS, yes, when P is equal S. And then this space coincides with the classical Lebesgue space LP defined with respect measure mu. Okay, so these spaces are, in fact, Lorentz spaces are also called the Lorentz scale because it is related also with Lebesgue spaces by such an embedding given here. Okay, and they are more precise spaces than Lebesgue spaces. For example, Holder inequality holds by such a formula 0.3, and it is a Banach function space, in fact. And now our result about characterization of measure mu to have the boundedness of a multilinear fractional integral operator. Just a moment. Lasha seminar zevarta tagireka. Okay, so we have the following statement, theorem. So suppose that gamma it is between 1 and infinity, and we have this indices here, Rj, Sj, between 1 and infinity. J it is from 1 to m. Suppose that R it is the number, it is an exponent given by such a formula. S it is a number, it is just the parameter given by such a formula. We assume that we have also parameters, exponents of the space P and R, where R is less than P, and also P, R, P, R, S, and Q are related by such an inequality. Then this inequality, 0.4, with the constant C of independent of Fk, holds if and only if mu it is upper alphas beta regular, where beta it is just this number here given by such a formula. So this is in fact necessary and sufficient condition for inequality 0.4. So in particular, we have the following criterion for the Sobolev inequality in a multilinear setting. So assuming now that everything is the same, but here we assume that P and R, they are related by this condition, which means that P it is a Sobolev exponent of R. Okay, then this inequality here holds if and only if mu is alphas upper one regular, which means, of course, that mu P XR is less than or equal some positive constant B0 independent on X and R multiplied by R. So this is a necessary and sufficient condition for this Sobolev inequality. Okay. So in linear case, when M is equal 1, then this operator, as I mentioned, it is given by such a formula, and we have the following statement that when when we have four parameters P, R, S, and Q satisfying these conditions here, okay, then this inequality here with positive constant C, here is misprint, this inequality here holds if and only if mu is alpha force beta regular given beta given by such a way that it is Rp 1 minus gamma over Rp plus R minus P. So in fact, the condition depends only on parameters P and R, and it is independent on parameters S and Q. Okay? And here is Sobolev inequality characterization for in the linear case. So this inequality where P is a Sobolev exponent of R holds even only if mu it is alpha force 1 upper 1 regular or satisfies this condition here. Okay. So taking now, for example, on Rn, if we take Riesz potential operator, but defined with respect to measure with a measure nu, so we have here measure nu. We have the kernel singularity, the same singularity as for the Riesz potential operator. Okay. Then we have the following statement for theorem 4 prime, which is in fact a Sobolev inequality characterization for this operator I alpha nu. Here we have measure nu and characterization of measure nu defined on Rn. And when P, it is just Sobolev exponent, then this inequality here holds even only if nu, it is upper alpha force n regular, which means that this condition it is satisfied. So for this special case of kernel, when we have x minus y to the power alpha minus n for this kernel, we have this criterion for the Sobolev inequality. This condition, it is just necessary and sufficient condition. So we studied the same problem in Morrey-Lebesgue spaces, Morrey-Lorentz spaces. I would like here to mention that Morrey spaces introduced by Morrey in 1938 play important role in the study of regularity problems of partial differential equations. And in the last 2 decades, considerable interest of mathematicians was attracted to the study of these spaces. For example, about the history and the results of harmonic analysis in these spaces can be found in 2 volumes monograph Savano, Di Fazio, Hakimov, 2020. Okay, and the boundedness of integral operators defined in Morrey spaces, but on non-doubling, on non-doubling quasi-metric measure spaces were studied by Japanese mathematicians Savano, Tanaka, also by us, by the speaker with Eridani and Kokilashvili. We had also results regarding the trace inequalities, regarding the characterization of measures for the boundedness of fractional integral operators. Here it is given the definition of the Morrey-Lorentz space, but a little bit modified, because here we have 1 over the norm, Lorentz norm, K by B. B is a ball, but here we have modified. This is a modified. In the classical Morrey space, we have here divided by we have here B, but when we study the problem for in the case of non-homogeneous spaces with non-doubling measure, then we have such a norm here, and we have such a statement which gives, in fact, but in this case, unfortunately, we have only sufficient condition on beta. And the same condition on beta which we had above guarantees, in fact, the boundedness of this multilinear operator from the product of Morrey-Lorentz space to another Morrey-Lorentz space, okay? So this was the first part, what I wanted to deliver. The second part, it is just Olsen's inequality. What is Olsen's inequality? In literature, Olsen's inequality, it is called the following bilinear form of the inequality. Here we have I alpha Riesz potential operator. It is multiplied, we see here, by G. So we take this potential of F multiplied by G, and we have the norm, function norm, which will be clarified later, and less than or equal by C, which is independent of G and F, and we have on the right-hand side such a product. Okay, as usual, X, E, and F, they are Morrey norms in Morrey spaces. Such type of inequalities turned out very useful in partial differential equations. In particular, let me show you Olsen's in the Olsen's original paper. The importance of such an inequality arose when he studied this perturbed Schrödinger equation given by such a formula 0.8 with potential V. But he studied this problem on the ball in a three-dimensional space, in three-dimensional space, and solved this problem and made optimal estimations of the solution in Morrey spaces. And for when he studied the problem, such an estimate was important, and he established, in fact, such an estimate in R3. Okay, in the frame of Morrey spaces. It was later by Japanese mathematicians, they improved this inequality, but our aim, but in their papers, it was not given a sharp estimate. I will clarify later what does it mean, sharp Olsen inequality, what we mean, okay? So we are interested to establish Olsen inequality in the multilinear form. This was the first our aim, but the result, sharpness, was in fact also new for a linear case, for a classical Riesz potential operator, and this was in fact our aim. So to establish Olsen inequality in multilinear form and to investigate the sharpness also of that inequality. Okay, and now what we mean in the multilinear form, Olsen's inequality has the following form, you see here. So we have I alpha operator, multilinear fractional integral operator, which we defined above, okay, multiplied by function g. It is taking here the Morrey norm, so less than or equal the norm of g in the Morrey space. And here we have the product of F1 and so on, Fm. Again, here we are given Morrey norms in Morrey norms, okay? And let me now, yes, also we studied for bi-alpha, for that bilinear, the problem we studied also in the for the bilinear operator B alpha, which is given by such a formula, which was introduced by Grafakos initially, okay? And now let me yes, what we mean under this Morrey norm LQR. in Morrey spaces, norms can be written in various form, but in our statement, it is given by such a norm. It is defined by such a way that the norm of f LQR. Here it is LQR, two parameters, where Q is less than or equal than R. So this defined with respect to measure mu, okay, in general measure mu. It is given by such a formula that so we are in Rn in this case. In this case, we are in Rn. At mu, it is just a measure. Let's say some Borel measure defined on Rn. And this norm, it is defined as follows. The supremum, 1 over Q is a cube, the volume of cube to this power, integral over Q. Here we have the Lebesgue norm of f with respect to mu over Q, okay? And supremum, it is taken over all cubes with sides parallel to the coordinate axis. And if the mu is absolutely continuous function, this means that the mu, it is just v dx, where v, it is a weight function, almost everywhere positive locally integrable function, then this Morrey norm we denote by LQRV, okay? And now, so here are some known results regarding the boundedness of fractional integral operator in Morrey spaces. There are, but in unweighted case, classical results, there are known two such results. Spanner result, which gives the boundedness of fractional integral operator, Riesz potential operator from one Morrey space to another Morrey space, and also the well-known theorem by David Adams. Okay, again given, but this is another statement given the boundedness of fractional integral operator. So everything this was done in a linear case for the linear fractional integral operator, and in the multilinear setting, the boundedness of the fractional multilinear fractional integral operator was given in this form under these parameters, okay, and it was established, of course, in unweighted case in Rn for the Lebesgue measure. Okay, they are classical results. Let me now remind you the statement by David Adams about the trace inequality for fractional integrals. In particular, by David Adams was proved in 72 the following important statement, which says the following, that when p is less than q and alpha it is between 0 and n over p, and mu it is a Borel measure on Rn, then this inequality here, I mean that the I alpha it is bounded from LP, defined LP, it is Lebesgue space from LP we defined with Lebesgue measure. So this inequality, and here we have LQ, Lebesgue norm, but with measure mu, okay? So from Lebesgue, classical Lebesgue space into another Lebesgue space with measure mu. So this inequality holds if and only if measure mu satisfy such a condition which is given here. This is the transparent condition, and this is the classical result by David Adams. And that statement in multilinear setting was derived by the speaker in 2014. When measure mu, it is absolutely continuous, and we proved, in fact, that the following statement, that when p is less than q, then this inequality here in Lebesgue spaces, okay, holds if and only if the following Adams tape condition it is satisfied. for a weight function V. In this case, as I mentioned, V mu, it is absolutely continuous, okay? And this condition, it is necessary and sufficient for this multilinear inequality, for multilinear fractional integral operator I alpha, okay? And now about our statement for Olsen inequality. So when we take now Morrey spaces, when we take parameters, okay, since we have more spaces, we need also, of course, more parameters. P is less than Q, where P it is given by such a formula. Q it is a parameter which is greater than P. Okay, alpha it is between 0 and over S. And these parameters are related by such a condition. Okay. Then the following inequality holds. The following inequality holds. You will see here there are given Morrey norms here, and this estimate it is sharp in the sense that here this function, this norm here cannot be replaced by the smaller Morrey norm. So in the frame of Morrey spaces, this is the best possible inequality because we cannot replace this by the smaller norm. As I mentioned before, this problem started, but those estimates were not sharp. But now here we have sharp estimate. Sharpness, we mean that in the frame of Morrey spaces, we cannot replace this inequality by the smaller Morrey norm. And okay, this is the consequence of that statement, which is new. Which is a very important corollary, and in fact it gives a complete characterization of those weight functions V for which this inequality holds. So this inequality here for multilinear operator I alpha, it is holds if and only if measure mu, weight function V satisfies this condition here, David Adams condition here, okay? So this was the consequence. As I mentioned, that statement, sharp Olsen inequality, it is new for the linear case as well. In the linear case, Olsen inequality has this form, and so we proved this inequality. And again here, this norm here, it is sharp. I mean that this norm for G, for this factor, okay? Okay, so let me now mention that, as I mentioned, we also studied such type of inequalities for bilinear operator by alpha, okay, by alpha, and now let me now pass to the last part of my talk. So this is the multilinear, one-sided multilinear fractional integrals. What I mean by one-sided fractional operators, multilinear. Okay, so we are interested to characterize such inequality here. We have on the left-hand side multilinear one-sided operator R alpha defined on vector function f So with components f1 and so on fm by such a formula. So we have integral from 0 to x. We have m times this integral m time. We have this set of integration product of this interval 0x by m times. We have here, you see the product of f1 and so on fm, okay, and divided by t1 plus tm m minus alpha. So this operator, and we are interested to characterize this inequality. In fact, what is it? This is a boundedness from unweighted product of unweighted Lebesgue spaces to the weighted Lebesgue space. Okay, so now this operator R alpha here was introduced in the paper. I hope that I have in the literature. This was not invented by us. It was introduced by another paper by another authors where they studied the boundedness, unweighted boundedness for that operators. I forgot the names for those authors. I have in the literature. Later I will tell you. But when we take alpha is equal m, then this operator R alpha, it is just multilinear Hardy operator, which has the following form. This is a Hardy operator in the multilinear setting. And when m is equal to, the just two-weight characterization for this operator in Lebesgue spaces was studied by the following authors, okay, which are given here. Two-weight characterization, okay. Our operator R alpha, a multilinear one-sided operator, yes, defined on a vector function. In the linear form, when m is equal 1, it is just the classical Riemann-Liouville operator. So from 0 to x, phi of t over x minus t to the power 1 minus alpha, okay? Classical. What is known for this classical Riemann-Liouville operator? When alpha it is greater than 1. So this is the case when we don't have here singularity, yes? Okay. This characterization of two-weight characterization was given by Stepanov. It was at the end of 80s of the previous century. So in the singular case, when alpha it is between 0 and 1. So it turned out, of course, more complicated. So unlike the Riemann-Liouville operator for the singular case, I mean that if we take integration here from minus infinity, sorry, here should be from minus infinity to x, yes? This two-weight characterization, it is known, it is well known, but when P is less than Q, it is known. But for this case, when we have singularity and we have R alpha from 0 to x, when it is defined on semi-axis, yes, two-weight solution of the problem. I mean that the characterization of weights from one weighted space into another weighted space is still open, but it was given such a characterization, necessary and sufficient condition on weight V from LP, unweighted from unweighted to weighted space by the speaker. It was in 1998 and independently by Prokhorov in 2001. And so the history and other related results are given in the monograph by the speaker jointly with Edmunds and Kokilashvili. It was published in 2002. And now let's come back to our operator in the multilinear setting, okay? But it can be rewritten also in this form, okay? In fact, this is the one-sided version of this operator which we discussed above, Okay, this is the Riesz multilinear Riesz potential, but this is the one-sided version of this operator. Okay, and let me formulate now the statement for the operator R alpha. When we have indices P1, PM, Q related by these conditions, okay, alpha it is greater than m minus 1 over. So in fact, it involves some singularity here. Okay, then the following statements are equivalent. So we have this weighted inequality, and the following, and the second, this condition on V, it is satisfied, this simple condition, or this is equivalent to write that condition in the following form. Okay, so in fact, this is a complete characterization for of this inequality in terms of weighted function V, Okay, so in Lebesgue spaces, it is characterization in Lebesgue spaces. Okay, as a consequence, we have in fact that result which I mentioned by the speaker and independently by the Prohorov for the Riemann-Liouville operator. So this is a Riemann-Liouville classical Riemann-Liouville operator, and this characterization it is given by such conditions which are given here. Okay, the following statements are equivalent. Okay, you see here. Okay, so and finally, let me say about references. So that last part, it was accepted in publication in the journal Mathematical Methods in Applied Sciences. So just today I signed the license of copyright license. Okay, it is not published yet, but it has DOI. So this the first paper about Olsen inequality. It was published in electronically in 2003, but in the hard copy as a hard copy in 2004. Jointly, it was done by jointly with Lucas Grafakos. Next, here are given some other papers also related to my talk, and let me now tell you that those results will be also included in the monograph, which will be appeared in 2025. This of these four authors here. Jointly with Gogilashvili. Gogilashvili is my teacher who passed away 2 years ago, but we started to prepare this monograph when he was alive. That's why we will have all of these authors will be kept. And this is volume 4. This is volume 4. Volume 3 of that monograph was published last year in 2024. And this is in Birkhauser-Springer. So 4 volumes in Birkhauser-Springer. It is this monograph. It is devoted to integral operators in non-standard function spaces like variable spaces, variable exponent spaces, grand function spaces. But here are included also related results about multilinear analysis. Okay. Here are given also some the papers about fractional integrals in on non-homogeneous spaces, pioneering results. In fact, okay, and some about multilinear fractional integrals are given on this page. Okay. And let me stop here because, as I mentioned, I have to run to my lecture. And thank you for your attention. Thank you.